In this video, we're going to talk about the concept of alcohols behaving as acids. So what is the definition of an acid? An acid is a proton donor. So if we consider ethanol, the C2 alcohol, ethanol essentially has three unique type of hydrogens. We have the hydrogen bonded to the oxygen, that's the alcohol proton. We have CH2 protons and CH3 protons. Each of these protons has a pKa value. Recall these are approximately 50 for alkane. This alkane is going to be approximately the same at 50. However, this hydrogen is going to be significantly lower at 16. Why is it so much lower? Essentially, when you treat this alcohol with a base, and I'm going to use sodium hydride as the base. So here's our structure of hydride. It's going to irreversibly deprotonate that. So using the curved arrow formalism, the arrow starts at the region of electron density and will end near the region of electron deficiency. So I've shown that using partial positive and partial negative charges. Since we are forming a hydrogen-hydrogen bond, and hydrogen can only have one bond, we have to break this oxygen-hydrogen bond. The electrons in that bond are then going to end up on the oxygen. So oxygen starts with its two lone pair and it ends up with a third. So overall it bears a formal negative charge. So we know the byproduct is hydrogen. That's a gas that escapes the reaction. So we need to account for this negative charge and balanced charge. So the only thing that can do that is the sodium cation. So this molecule is called sodium ethoxide. So why do we form these ethoxides? So basically we're going to use this in a reaction to make an ether. So specifically the Williamson ether synthesis. We're going to take our sodium ethoxide and treat that with an alkyl halide. Let's treat that with ethyl bromide. In this reaction, we have a molecule with electron density, so we're going to call that the nucleophile. And then we have a molecule that is bearing a carbon that's electron deficient. So I've put in the partial positive charges, And I've got this from the periodic trend of electronegativity. So we can represent that as a dipole moment like that as well. So this molecule is classified as an electrophile. When you mix these in the reaction, it's going to undergo an SN2 mechanism. The curved arrow is going to start at the electron density and attack the carbon bearing a good leaving group. So bromide will then leave. This is an SN2 substitution nucleophilic bimolecular reaction. We're going to end up creating a new carbon-oxygen bond. So we've created this bond. This is an ether. We're going to name that diethyl ether.